Can you hear me now?
Yeah, we can hear you, sir.
Okay, thank you. There's some problem with my earphone. Sorry about that. Okay, so today we will be discussing the difference operators, which is typically used for edge detection and all. And we'll go through this canny edge detector and some blob detection things, and finally the sift, right? The scale invariant features. So that's it for the today's agenda. I mean, the on the practical side, this is what we will go through, and we will solve some problems. Um, can you come again? Yeah. So, and we will solve few problems. Post that, and yeah, and that's it for today. And today also we will not go into the deep learning part. So I think from the fourth week onwards we will have neural networks starting. So I think the third week also we will have the traditional image processing part.
Sir, what
Okay.
we hello.
Yeah. Please.
Sir, in the week two, what happened was scale space, image pyramids, and filter banks.
Right. Yeah. Yeah.
And
Those
we
practical
discussed,
aspects we will go through today.
yeah, in that specifically, we have discussed about Gaussian pyramids and a difference of Gaussian pyramids,
Yeah.
then
Yeah.
texture detection
Okay.
using histograms by considering the weightage of global text orientation and
No, we
other.
will not have a practical thing on text detection. We'll only have, um, um, I mean, the regular operators, difference operators, canny edge detection, and certain sinusoidal and Gabor filters. I mean, visualization of those filters followed by the sift, right?
Okay.
Yeah. And yeah, post that, as I said, we have to solve six problems. We will solve six problems in every session. that can aid you in your assignment solving. Okay, I'll share the screen. Please let me know if you can see the screen.
Sir, here, if you don't mind asking some of the doubts that happen in the runtime classes
Um, you
related to
can
key.
ask. Yeah, you can ask, but yeah, I might not be able to answer all of them. Yeah, whatever I know, I can. But yes.
So, is there any way
Um,
to the process that we can directly communicate or drop the questionnaire or doubts to them?
if you have the questions, right, you can write. You can post in the chat. If say
Oh,
if you have some questions and I cannot answer, you can list it down and post in the chat. Okay? I'll try to answer them the upcoming week.
okay,
Is
okay,
that good?
okay. Yeah, fair enough.
Right? Yeah. So if anyone is waiting, please allow them. Okay. You can see the notebook, right?
Yeah, we can see the notebook.
Yeah. So we'll go through the Sobel filters. So what is a Sobel filter? I mean, it's a high pass filter or a low pass filter?
Sir, to be frank, it's been a while I taught the subject, really not in touch since 1 year. But it's better if you can give us a brief about it and then if you can go ahead. Of course, better to ask the question. I'm just talking about only myself.
Yeah.
Because
Okay.
last time we had the same problem. There was some expectation bar was a bit high. So it was little, it was at least for me, I thought I should have prepared something and came and attend this class.
No, I did not get. You want me to go slow or faster than the last time or
No,
slower than the last time?
pace is correct, but some of the dependent knowledge base, either we are not in touch with the subject or maybe some of the folks in the group may be totally new to the subject. So myself, I've already taught a year ago, but I have really lost in touch with the subject. I came here just to upgrade my current status or advanced features in the computer vision. Of course, it's expected to read and come back, but there is a limitation on us. Though we are working, to what extent we
That's
should prepare
fine.
and come to this class.
That's fine. I mean, that's fine. Um, we don't expect any prior background except from the coding point of view because I cannot go line by line and explain the code,
No, sir,
right?
no, sir.
Um,
What we can do is you just explain the concept. In the concept, maybe there's some couple of points, maybe key points, without which there is nothing is going to happen. That logic, if you can able to explain, I think most
okay.
of them, they can
Okay.
people in the
He means, I think he means to say just if you can revise on a high level.
yeah,
Understood.
exactly. Start with the
So
concept, and then you can just correlation to the code that would really help us.
okay. So what? Okay. So today, bear with me. Just today's week. Next week, what I can do is I will summarize whatever has been taught by the professor.
Yes, sir, because a lot of questions, even though I have went through some couple of times, still I was not clear. So that's the reason I asked this question.
Fine, fine, I got it. So from next week onwards, let's do it. Let's revise the theory part first. Maybe
Yes, sir.
five six,
Yeah.
and then we'll do the programming assignment followed by the problem solving session. Okay.
Okay. Okay.
Yeah, but today just bear with me. Today we just let's go. I mean, on the fly, I'll try to explain whatever I can. But yeah, just bear with me for the today. Okay.
Okay, sir.
Yeah. So first we'll go through this Sobel filters. I mean, any idea that this is a low pass filter or high pass filter? So typically typically this is something like this.
It's a high pass filter, right? It's used to detect edges. The high frequency components it allows.
Right, that's true. So this is a high pass filter, right? This is a Sobel filter, and just remember, whenever you see a operation, right? That's a high pass filter. And whenever you see an averaging operation, that's a low pass filter. It's true in general, because this is a high pass and averaging is a low pass. Any averaging is a low pass filter, and typically any difference is nothing but a high pass filter, right? So that's the logic. That's the reason we say this is a high pass filter, and yeah, so it is detecting edges in this direction, horizontal direction. So vertical edges are detected in horizontal direction, right? And they have similarly another the same thing in the y direction. This is a filter. Okay, so this finds the edges in the vertical direction. Okay, in this direction. The vertical, I mean, yeah, this, and yeah. So, by the way, are you people able to download the notebook and able to run of the first week notebook?
Yes, sir. I was able to run them.
Yeah,
They're
and
working pretty fine.
okay. Please just try to understand this function. Some simple functions that are important if you want to implement something on your own. That is important notebook. And here, this is ready-made implementation, but yeah, that's the basic part, which you guys should know, right? So yeah, this is um, we download an image. I think that's an image of a nebula, and we just convert this to grayscale. Okay, so
Sir, another suggestion I have, if you don't mind. Sorry to
yeah,
interrupt. Week one assignment we have already submitted, but if you can just revise a moment, so that of course marks is of course important, but to be make it as a complete understanding, if we could able to discuss the week one assignment answers and its relevance to the answers, that would really help us, even though we have marked some of the answers as very doubtful with our knowledge.
so we can do one thing. Um, let's pick out of I'm solving 6 questions, right? Let's do one thing: 5 questions on the current topic and 5 questions from the previous the prior weeks. This thing.
Yeah, as actual assignment, if you could discuss, at least for the knowledge completion sake, we have some confidence level why that answer is really that answer.
Actually, I don't know if I can do that because they were saying that we cannot discuss the assignments.
No, it's already week one assignment. Last date is already over.
Yeah, I'll just check with my this thing in the
Okay.
group which I have if I can. Yeah. Otherwise, I could just discuss the week one assignment itself, right? That would be better in the problem
No.
solving.
Yeah. Anyway, the date of submission is over. Now it is for
And I
completion
got
sake.
it.
Probably we could.
I got your point. Yeah, I got your point. Is it necessary to learn sklearn? Sklearn is nothing actually. Sklearn is you need to know what are the tools that sklearn does for you. It has everything inbuilt. You just need to invoke the function and this thing, right? Pass the arguments and get the output. So all you need to know is sklearn anything is like that. You just need to know what are the functions that sklearn supports and where you can use it, and nothing beyond that. It should not be difficult. sklearn should not be difficult. You can look up to their original page. I mean, it's very 2-3 liner. That's it. SQL. And if you see going forward, when we come to neural networks, it will be even easier.
Sir, if you don't mind, like, can we first finish the content, the live session, and in the end, take up all these questions?
That's how I'm also fine with that. Yeah. Maybe let's do it, right? Let's quickly finish.
Yeah, let's
Finish it.
first finish this live session instead of,
Yeah.
interrupting it.
Yeah. Yeah. Okay. So, yeah. So these are the Sobel filters. And see, the reason this is GX is called it is GX because it detects the edges, vertical edges in the X direction. I mean, and this is GY in this direction, and it detects edges, the horizontal edges, basically. Right. So yeah, just pass. This is just a straightforward implementation of the Sobel filters GX GY, and we find the overall response that is given by the magnitude of GX square and GY square. I mean, the square root of GX square plus GY square. So that is what is being plotted here. So to be precise, what we have done is we have computed GX using this on image to get GY. So basically, this is nothing but an image. Each pixel is in this image is denotes the gradient at that point. Here also it denotes it's an image, but the entries are the gradient in y direction. The overall, what we have done is we have plotted this igx square plus igy square.
Something like a magnitude.
Yeah, it's magnitude. Yeah.
Okay.
And
And we reconstruct the entire matrix.
no need to reconstruct it. It's just the magnitude of this gradients is what we have plotted here. Here. No, sorry, not there. But yeah, I think it's coming up. Still working.
Sir, one small doubt. Is there a way to combine the X gradient and Y gradient into a single kernel?
Um, Not that I can know of.
Okay,
I
so
can.
we have to do it separately.
Yeah, yeah.
Okay.
So there is something called as a Laplacian. Maybe that's what you are referring to. We'll see.
Yes. Laplacian, we do it together.
Yeah.
For
No,
other methods like Sobel and Canny edge detector and all, can
I
we do it
doubt
using
that.
a single kernel, or should you do separately for X and Y?
I think separately only will do.
Okay.
Okay. Okay. So let's go to the canny edge detector quickly. So this is the algorithm. Okay. Filter the image with the derivative of Gaussian, and that's the first step. And post that, you find the magnitude and orientation of the gradient. Then we suppress the low values uh, from the step 2, and in the step 4 we try to link the necessary pixels that may contribute to the edge. This is the overall algorithm of the canny edge detector. And yeah. So the first question is, why do we need a Gaussian here? Why can't we just apply a Sobel filter, a derivative filter such as Sobel?
So Gaussian will actually smoothens out image.
Yeah. So what it does?
That maybe if the noise exists, may eliminate.
Yes, that's the correct response.
Also,
So
in Sobel, we don't do this non-maxima suppression and linking and thresholding, right?
I don't know. No. So what I'm asking is, the moment you say derivative, it's a sort of an approximation to. You can view that as a Sobel filter, basically. The
Okay,
derivative
okay.
operation is Sobel filter. What I'm saying is, before taking a derivative, we are doing a Gaussian kernel on an image. Why do we need it?
Yes, to smooth out the noise.
Right. So typically real world images are we capture with a noise, and with that, if we simply take derivative, we may end up having false edges, false responses. So for that, we first smoothen out remove the high frequency noises components through a Gaussian filter. Now Gaussian filter is here acting as a low pass filter. Okay. And then we take the derivative. That is, derivative is nothing but the Sobel x or Sobel y direction. That gives you the true, I mean, a better edges. Right? Let's see the first step quickly. Now we have a Gaussian kernel, and there is image. I haven't yet applied the kernel. So yeah, so this convolve operation is being imported from SciPy. Okay, so we are not writing. I advise you to not to write always. Reuse the existing thing. So it's good to write once, but yeah, if we have existing tools, it's better to use them. Okay. So yeah. So what happened from this to this? Right. So
Smoothing.
it is blurred. Exactly. Yeah, it is blurred. So here we sort of remove the noise from this image. So we don't get the false edges. Right now is the way we implement the this thing, the Sobel operator, right? KXKY. Just it's nothing but creating the kernel, what I have written here, this one, and apply the same thing, convolution operation. This is imported from SciPy, and I think this computes the gradient at ix square plus iy square, and we are normalizing it to the max value of 255. And this is nothing but the angle, the orientation. That's it.
Sir, can you print a theta dimension
Same, it will be same as the image.
as IX input image?
Yeah, yeah,
Okay.
yeah. Because we are visualizing them.
For every pixel, we are determining the.
Yeah, yeah, yeah. So this is the image of the gradient magnitude, and this is the phase information. And we will end up using both, if I'm correct.
Sir, I have a small doubt. So is
Yeah,
it mandatory to always convert the image to black and white or grayscale before doing edge detection?
typically we do this. I think so. Yes.
Okay.
Yeah. And yeah, so basically what is this non-max suppression is doing is, post we have let's say we perform this dog, right? Sorry, Gaussian and the derivative of Gaussian, right, on an image. First you low pass filter and you do Sobel, right? um now you have this thing, right? The images gx square plus gy square, and we have the theta. So now what we do is, say we pick any pixel x, let's say, and now we see the angle of theta corresponding to this x, and we retain this x if its magnitude is greater than this pixel and this pixel, the neighborhood pixels, right? So that is what is this operation is doing, non-max operation.
So that means all those neighboring pixels, those edge pixels whose neighbors magnitude is less, then they're suppressing.
Yeah, because
Okay.
if this magnitude is more than this, probably this is the
Whatever.
edge, not this. Yeah. And yeah, so final step is the thresholding, and we will remove the lower, the, the very low values, and so basically it is something like this. So there are two thresholds. So this is something low, and there is something called as high threshold. Anything above high is a valid point. I mean, valid point in that edge map. Anything below low doesn't contribute. Now, what do you do? What do you want to do with a bit that is between the low and high, right? So, what you do is typically, um, if any pixel is between say low and high, except some pixel if it is between low and high, and you want to classify whether you should discard or you should accept here. So if there is a high pixel in its connected component, so most likely it is assumed that x will also be a high pixel, right? So this is what we are doing here, this and the hysteresis definition. So this is just checking the connected components. If you can see, right? I think probably it should be 8 or something. 8 conditions.
Oh, that means for all the edge pixels, it will check all the connected components and
Verify the condition, right?
condition, and then add them as a edge.
Right.
Okay.
So yeah, this is the final this thing. Right. And yeah, you can go and read about this. Here, the reference is provided. I'll upload the notebook later. Later, maybe before Monday, I'll upload for sure. And yeah, so this is just a visualization of sinusoidal wave. Okay. Now this is a Gabor filter. All right, it's a Gaussian modulated by a sinusoid, plane wave basically. Now this is an implementation and visualization. Now my one question to everybody is, we have sinusoid. I mean, I can see similar intensity here, right, across the diagonal, right?
Yeah.
Why there is not? Why that's not the case here? Why I have only here and something here, something here?
So can you repeat the question?
Question is, for a sinusoid, I can see say ones and high values, low values, high values, low values, right? The intensity of the value here, this line, you can see the arrow, right?
Yeah.
Is same as here, and it's same, and it is same here, same here, same here. But here, this the intensity is high, and here it's low, and it's almost died down here. Why is that the case for the Gabor filter? Hint is here.
We are using here the size of the Gaussian is different, right? Like
Yeah,
there is
what's
a
happening?
sigma component that is actually standard deviation of the Gaussian envelope we use.
Yeah, but so whatever is the standard deviation, it may. Okay, so let me answer
Because
that.
the bigger the deviation, the bigger the size cells it will
Yeah,
display.
what you have said is partially true. The reason is this, right? See, Gaussian. Sorry, it's not. So you can find this can also be Gaussian. Let's say with some mean. It is falling off with e power minus x square.
Yeah, e power minus x
Minus
by
x square by 2. Our sigma square is depend whatever is the sigma square, but the rate of fall is of the order of this thing, e power minus x square, which is super fast. If I take x to be 10, let us say, right, and sigma square to be 1, right, it is e power minus 100 by 2. You can't even imagine. I mean, it is e power minus 50. Right, it dies down that fast, and when it dies down, there is nothing sinusoid. You don't see it basically, so it exists very in a smaller neighborhood, and that's why its shape is like this. Okay, so we generate this filter banks in different orientations. For that, you can see the code here. By the way, this what kind of filter it is? This Gabor filter, right? It is something like this, right? Say we consider a simple one-dimensional thing, right?
It's a low pass, right?
Yeah. It's not exactly low pass filter. Multiplied, say, sine 2 pi ft. F naught is some fundamental frequency I have given. Okay, this is my one-dimensional called one-dimensional Gabor filter. Right? What kind of filter is this? Yeah, so these kind of questions you might end up, I don't know, but yeah. I'll just wait for 30 seconds and I'll answer.
So we kind of multiplication we're doing it, so probably a low pass filter.
No, it's not low pass filter. Under to measure high values to low values. Yeah, I mean, we have to measure anything between high and low and check if it is in the connected component. If there's anything that is in connected component to high value, declare it as high. If not, declare it as low. I don't know if that was in the context. Yeah, I think 30 seconds gone. Let's answer this question. Okay. So e power minus pi t square is decays super fast, and it is something like this. It's Gaussian, right? E power minus pi t square. So to the best of my knowledge, I think this is the only signal which has the same frequency response. This is x of t. If I say x of f is e power minus pi f square. Maybe some constants can come in here, but yeah, this is the form. Okay, so it is something like this. The sinusoid has I'll just plot the magnitude, two impulses at f0 and minus f0. Because it is multiplication, it's convolution in frequency domain. Right? Impulses, when you convolve, it just shifts. Right? The Gaussians now centered at f0 and minus f0. Right? So this is a band pass filter. Okay. Yeah, this is how we should think. But yeah, the key here was you should know that the spectrum of e per minus pi t square is same as e per minus pi f square. To my knowledge, I think that's the only thing which has the same form. I don't know. There are other signals which has same frequency response as the original signal. Okay, so then this is an alternate way of doing the same thing. Yeah, this is now we'll go to a blob detector. Basically, blob detector is nothing but the Laplacian of Gaussian, right? That gives the blob, detects the blob. Basically. Right. So here it's not the. I mean, we have to uh, play with different sizes, right? Then it detects the blob. Basically. Yeah, I don't have a slide to show the true visualization of that. What should I say?
So
The
just
Laplacian
before
kernel.
going, sir, just sorry to interrupt. Before just going to the next, in the Gabor filter, the wavelength of sinusoidal component is actually proportional, right, or inversely proportional.
I didn't get. What do you mean the wavelength?
See, the equation of that Gabor filter is g of x comma y is having a dependence on variables like lambda, theta, psi, sigma,
Yeah.
and gamma.
Yeah.
So which is equal to e exponential inverse proportional to x prime square plus gamma square into y prime square divided by 2 sigma square
Yeah.
into e in and complex component.
Yes.
So how do we analyze if there is more than two parameters are there in such kind of components? So how did you arrive at that this is actually resembles like a band pass filter? I was a bit confused.
I mean, I have analyzed this in the single domain, time domain.
Correct, but if
Right.
you can, we analyze in single domain, but this because it has a component like exponential, inverse exponential component, so it's more or less behave like a band pass.
Yeah. So basically, see, I freeze everything else apart from x and y.
Okay, so they are a variable.
Yeah. So for every lambda, theta, psi, sigma, gamma, you get some kernel, right,
Yeah.
which may have its own this thing. But I freeze them. Right. With them frozen, I view g of x comma y as my spatial filter. And now given all these variables, what I was asking was this g of x comma y with our specific values of lambda, theta, psi, sigma, gamma. Is it band pass filter or low pass filter? Well, what I'm claiming is it's a band pass filter. For this, I have shown the proof in one dimensional, visual proof.
Okay.
Okay, and yeah. Yeah, basically, a blob detector is nothing but the Laplacian of Gaussian operation. We need to take this typical, I think, Laplacian of Gaussian is what? Minus 4, 1, 1, 1, 1, zeros and zeros and zeros. Right. So this is a Laplacian of Gaussian kernel. I mean, its shape is something like this. How should I say? Something like this. Yeah, I cannot draw the 2D visualization, but it matches the response. It's something like blobs, right? Around here in this blob, you have a negative. I mean, the value is low, right? So wherever you have this blobs, you hit the maximum response in the output. So that's what it is detecting. So this is a 3x3. Similarly, we have a 5x5 Laplacian of Gaussian and 7x7, 11x11. Depending upon the size of the blob we need to detect, we can employ these filters. Right? That's what it's been doing basically. Like, these are different kernel sizes. Right? We are seeing the responses.
Sir, Laplacian by itself, all it does is detect edges, right?
Laplacian by itself.
It is
Yeah.
basically an edge detecting method. You compute the gradients and right.
Yeah.
You compute the second derivatives, and where there is zero crossing, you say there is an edge. So it's basically an edge detection method. So instead of using Laplacian of Gaussian, can we also use other edge detection methods like Sobel to find the blobs?
So basically, I'm not sure if we can use Sobel or not. The reason why we are able to find the blobs here is, uh, okay. Let me give you something. How should I put it? Let's say this is my. So this is my filter. Let's say h of t. Again, I keep going back to one-dimensional thing to clear out some of the intuitions, right? And let's say we have the image x of t, right? So it is, so the image has something like this, and something like this, and something huge, something like this, something like this. So basically, when you convolve x of t with h of t, we get sorry, we get the maximum response
भाई
when
लैपटॉप पे खोले हैं, ये 7 लोग अटेंड कर रहे हैं क्लास, तुम भी आना 7 लोग में से।
we mute.
जो एक लिंक आया होगा 4 से 6।
Sir, you can go to this mic and mute all. You can click, sir. There's a mic button is there, no? Come to the right on the top left, top right.
Okay. Yeah, I think there was some signal problem. Yeah, so coming back to that question, right? Why can we use Sobel or not? I'm not sure if Sobel can detect the blobs. the reason we are able to detect the blobs is the time domain response of the Laplacian of Gaussian has a contour of a blob, right? And depending upon the size of the kernel used, it gives the response maximally to that to that blob basically, right? So let's say if this is x of t, this is h of t, right? And the this part of the signal will be maximally activated with when you directly overlay this and this, right? At this instant you will have this maximum response.
Okay.
I mean, it's just an intuitive way of explaining things. But why it cannot other shapes cannot give you this thing? And yeah, yeah. So finally, we go to sift, and yeah, this is quite complicated one. I may not be able to go into every detail of it, but yeah, high level, I'll explain. So first we need to find the extremum points. Extremum points is the interesting points which are either too low or too high, or something like that. We'll see what exactly we mean by too low or too high here. And then we need to localize these extremum points. Not all of them can be useful, right? We need to find the best possible candidate points from the step one. Step three, we estimate the orientations uh, that are obtained from the key point localization. That's step two. Finally, we assign we get some for each of the points. Right, in step three, we get a descriptor. Descriptor means we assign some feature vector to each of this, right? So this is a sift in a very high level, and yeah, so this is how we need so many functions to implement. Right? All these are imported from NumPy, and from linalg you import determinant least squares. I believe this is a norm, and yeah, from CV2 for this you need to install OpenCV to run this notebook, and yeah, that's it. So here we get an image and just uh, remove the noise. We call this as a base image. This is an image of a copy, and compute the octaves. I'll quickly go over what do you mean by this octave and all here. Now we generate a different Gaussian kernels. If you remember, um, yeah, these are the different Gaussian kernels. Right. So let me take a step and go over briefly of this step one. Right? Yeah. So what we do here is we approximate the Laplacian of Gaussian with difference of Gaussian. Okay. So each image, I think this is what they are referring to octaves. Right? This is uh, Gaussian filtered with say sigma 1, sigma 2, sigma 3, and some sigma 4, let's say. Right now they compute the difference images and you get an image here. We get an image here. Here also compute the difference images and we get an image here. right? And for every point in this thing, so for every point, let's say pick this point, and how many neighbors we have here, right? Here is a 3 cross 3, 9, and 9 to 27, including itself, we have 27. But yeah, apart from that, uh, we have 26. So from these 26 neighbors, you retain this point as an interesting point or key point, whatever, if the magnitude is more than all of them or less than all of them, less or more. Okay. Yeah, so this point is at this point will be generating the Gaussian images, which means these images. You can see these are the blurred images, right? One. As you can see, I think the level of sigma is increasing here. You can see this is more blurred compared to this. So now this is computing the difference of Gaussian images. Okay, now we want to find the key points. So how do we find this key points here? If you remember, what was described in the material was you approximate this with say a Taylor series, some s naught plus s naught plus delta s. Right, something, and we optimize over this delta s, and that is given by your Hessian of this thing, that's not inverse, times the gradient. I'll solve this. I mean, I haven't put this question in this thing, our this regular problems, but I'll solve this. We get this. Okay.
So this Taylor series actually starts from self S0, then
Yeah.
delta into first order, then delta into second order, right?
Right. Delta square you get once you go to second order. That's why it's called a second order. You get second order terms.
So this Taylor series will also give me my x comma y coordinates as well as a scale, all three. Because
Yes.
x comma y
Yes.
coordinates anyway we determined with that key point, but for the
Yes.
exact true extremes to determine, it will give you the real delta.
Yeah. I think that's the case. Yeah. So let's see. If you can see this thing, right? We are computing gradients on the x direction.
No, my question actually lies there. How do I determine the first order derivative and second order derivative is my question.
Yeah, that's what I'm coming, right? So first order derivative is approximated by simple functions such as f of x plus h minus f of x minus h. In the pixel space, it is f of x plus 1 and f of x minus 1 with a gap of 2 pixels and average it over 2.
Okay.
So it is something like this. If we are at, let's say, position 2, and want to compute the gradient on this third axis, I'll look back and take the difference at 0. Okay. So it is over S, and it is over Y, and it is over, as you said, it is over sigma as well. Okay. How do we compute the Hessian? Hessian also we have the approximation, which is this, motivated by the actual this thing, Hessian.
So that entire array of first order, second order derivative, you do it for one scale above and one scale below.
No, I think only at the points which are written here.
Okay.
You do this operation for every pixel, right? And you do this thing only wherever these are alive at, not the
No,
0 to
so
0 out
after
point.
the second approximation to Laplacian, we
Ah.
get only the edge points, right? Among the edge points, we want to determine which are key points, right?
Right.
So within the key points, we want to find the true key points or true extremes.
Yeah.
So I'm still confused how they get the delta S with only the first order and because we are determining the delta of scaling for a from using first order and second order derivative of the special values, that coordinate values.
You can do this first order, second order for any vector, right?
Yeah, I understand X and Y, that first
Yeah.
order, second order, but how do they get delta S is what I'm still not.
Oh, you mean this delta S?
Third line, yeah, DS.
Uh, yes, it's probably over across this axis, because that is
Yeah,
where you.
across that axis. Now, which is that in between axis, we are determining the scale.
Yeah, I think it
So,
should be depending upon what you call as zero. I mean, um, it matters. Like, I mean, with respect to this, we are going here or here. If I
so
call this as zero.
in that case, once we are traveling in this vertical direction, that difference should be from one scale above, one scale below the x-axis difference and y-axis difference, right?
Right, right.
Is it true? Is what 211?
So you take difference of two, a gap of two, because I mean, you can approximate it with f of x plus 1 minus f of x, but numerically, when you do this, it is better at a point x. If you want to compute, you just subtract with uh, plus 1 and a minus 1 of that, and you
Minus one
differentiate it.
pixel and average it.
Yeah, it has better numerical properties. Okay.
Okay.
Yeah, and this is the uh, now post this. I think what is being done is we compute the orientations. And these are just the functions, right? Now after this step, we just
I think we remove or reject low contrast points or points that lie on edges. I think.
yeah, that is there. I mean, I just want to go over the key steps. Where is this? Yeah, the orientation estimation basically.
Yes. Estimating orientation. Okay.
Yeah. So here we compute the, I think this gx, gy of the image, I with the kernel xy sigma. On this, we compute gx, gy, and yeah, as you said, I think here we do the non-max this thing suppression.
Yeah, the edge points and low contrast points are eliminated.
Right. Right. And they remove duplicate points as well, if I'm not wrong. Yeah, so basically finally what they do is uh, corresponding to the points that we have obtained, the corresponding key points that we have obtained using the Taylor series, this thing, and we get this the map gx, gy, and orientation. Let's say the tan inverse of this thing, gy, gx. All right.
Yeah, yeah.
Now,
That's the
now
orientation
we,
of the.
yeah, now we want to have a descriptor of post this after this operation. So what they do is, I think in the actual thing, they take the 16 by 16 grid for every point. Right, for every point they take 16 by 16 grid, and internally they make it 4 by 4 this grids. I mean, correct me if I'm going
Yeah, yeah.
off.
They take a whole size of 16 by 16 and divide it into 4 by 4 components
Right.
of 16 total count.
Correct. And here I think they quantize the phase in 8 directions, in eight bins basically. And yeah, so, and they do depend this they do some heuristic scaling based on some Gaussian filter, right? um, yeah, and so each bin will have this what should I say, so 8 this thing,
8 values
8 values
or
in
8
overall will
orientations.
yeah, 8 orientations. So overall will have so 128. It's true, right? Yeah, yeah, 16 times 8. So for each of this remaining this thing k, we compute this and then we assign this 128 dimensional vector, right? So this is the overall sift thing. It is complicated, I agree.
Sir, just one question here. How do they really determine histogram based on the orientation as a metric? Because
uh,
regular histogram we studied is number of count
Basically,
as a pixels.
understood. So basically, if you have something like this, let's say this thing, it's a real value, right? Gradient.
Yeah.
So what they do is, say if it has some angle, if this angle is quantized to 1 of 8, right? If it has some angle, it is quantized to 1 of the 8 those things, right? And now once you have these directions mapped to 8 entries, so 0, 1, 2, 3, 4, 5, 6, 7, 8 entries, let us say all these angles are mapped to 8 entries. There can be some angles mapped which mapped twice, so it will be 2, something like this, 3, right? If
Okay.
these directions,
In the
something like
four
that.
among 4 pixels, how many of them are pointing to
Yeah,
second bin, third bin, or something like that?
correct,
Okay.
correct,
Okay.
correct.
Yeah, thank you.
And yeah, I mean, this is what it is. It is confusing. I mean, it's confusing. So I suggest read it, and if you have time, yeah, go through each of these functions. That would be useful. And yeah, so this is all today for the
Sir,
practical
is there
session.
any other method, just to say orientation estimation? Is there any other way? Because it looks too costly to determine the magnitude and the orientation.
Traditionally, I'm not sure because I'm not that familiar with the traditional image processing. Once you venture into deep learning, I think you don't need any of these things. I mean, you
Yeah,
let the network
nowadays nobody
decide.
talks about complexity of the algorithm because
Yeah,
of the GPUs have come into picture.
right. So you will
Yeah,
see that from fourth week
obsolete
onward.
topic to discuss about complexity itself.
Yeah, I mean, even these nobody is using these days.
Nobody using or nobody talking about all these things.
Right. This is just to set up the this thing. I think. Yeah, for from fourth week till the end of the course, it will be deep learning.
Okay, okay.
Right. Um. Yeah. So let's try to solve some interesting problems. Notebook I'll upload. Uh, Before Monday, I should be uploading this for sure.
Okay, sir.
Yeah. So yeah, I think last time I have presented an example of what is what when a kernel is not separable. Right?
Kernel
So
is
this is an
separable.
example of a separable kernel. Right? So let me yeah. Right. So this is a kernel 1 2 3 2 1 1 2 3 2 1. This is 5 cross 1, and this is 1 cross 5 matrix. Overall, it will be 5 cross 5 matrix. Okay, and the actual kernel given was this 1 2 3 2 1 2 4 6 4 2. I'm just multiplying this outer product. This product is called as outer product. If you are familiar with the matrix theory a bit. 2 4 6 4 2, and finally 1 2 3 2 1. This was the kernel that was given. So if the kernel is separable, it is something that you can decompose into this kind of thing. So the advantage will be the convolution operation gets cheaper in the sense first you
The
can
number of
convolve with
computations will drastically reduce.
yeah. So mm, this advantage. Now some simple questions on this is what is the rank of this kernel? Right. Any separable kernel will have uh, rank of 1, right? Because each is of rank 1 matrix, and the true vector is this. Everything else is obtained by multiplying with the entries of this vector, right? So that's why it has only one vector in this direction. Let's say some direction in 5-dimensional space. Others are obtained by stretching, contracting, stretching, contract. Sorry, this is independent. Others are obtained by scaling this, the same thing, shortening, increasing. And so this is a one-dimensional, the rank 1 matrix. And what is the determinant of this matrix? Any rank deficient
It
matrix has a determinant 0.
0.
And yeah,
Sir, using eigenvalues and eigenvectors, can't we determine whether matrix is possible to decompose?
what do you mean by decomposing is, I mean, when I say a matrix is diagonalizable, I say that it has eigen decomposition. But any matrix undergoes something called a singular value decomposition. Any matrix,
Okay. Okay.
right? So I mean, depends what you are referring to, the eigenvalue or the singular value or something. Right?
Okay. But which is better for
Yeah. So this is a
convolution? Similar value, right?
convolution.
Yeah. If you want to do convolutions, then it's better to decompose in a similar value.
No. Don't never decompose matrix. It's a very costly operation. Why do we want to decompose into? Why do we want to go into that domain actually? The eigenvalue or singular value domain. Why do we want to go?
No, just to see is better or cheaper way to decompose the matrices.
No, I don't suggest that. The easiest way I can think of, apart you have signal X, you have signal Y, signal H, and you want to do X convolution H, right? Uh, this itself is the cheaper way. Any other cheaper way I can think of is take the compute Fourier transform of X. Now it becomes multiplication, element wise multiplication, Fourier transform of H.
Yeah.
And the problem is again you have to take inverse.
Inverse.
That yeah, probably this might be costly.
Yeah.
This involves the entire image dimension. This thing multiplication.
Correct. Yeah.
And yeah, I suggest it's better never go that way. It is useful to obtain good insights, but even though if you have noticed in many of these things, we don't directly compute lambda 1 lambda 2. They call us trace and determinants, right? We never go in the domain.
Okay.
Okay, so yeah, so this is an image 456724032. 456724032. Now we are performing a linear contrastive stretching on this image. So what after performing this operation on say center pixel, what is the new value? And this is a 4-bit grayscale image. That means minimum is 0, maximum is 15. So the true this thing value to subtract with the image minimum, that we multiply with this thing, the max of the image level resolution, that is 4-bit, right? 0 to 15, 15 minus 0 by max and min of this image, the 3 cross 3 image, plus the lower value, whatever it is, 0, right? Yeah. So this is will boil down to 15 over 7. Right. I think maybe some similar question might be there in your assignment. So just yeah, pay attention here. And you may ask to uh, uh, round it off or seal it off to nearest values that you guys can do. I think 2.1 or something. So it will be 4.2. something like 4. And
yeah. Can you come again? Can you come again?
No, sorry.
Yeah.
So contrast stretching is only for center pixel or for entire image, sir?
It is for entire image. The question was what happens if you do on center pixel.
Oh, okay.
So now this is an interesting question. Okay, so let me, what was this? 2 minus 3, 4. 2 minus 3, 4, 7 minus 8, 5. Let's say some numbers, so 1, 3, 2. So this is an image, and the representation used here is 2's complement, 4-bit. That in 2's complement, if you have 4 bits, I mean, in general, if there are 4 bits, you can represent 16 varieties, right? That's the basic one, the 2 per 4. In the 2's complement also, you can represent 16, but the range varies. It is something like -8 to +7. Okay. So this is supposed to be treated as the most positive pixel, and this is supposed to be treated as the most negative pixel. Right. So in the contrast stitching, what happens? Most positive maps to most negative. Right.
Yeah.
So 7 maps to -8. Any idea where 6 should map?
-7.
Yes. 5 should map to -6. 4 should map to -5. 3 should map to -4. 2 to -1. 1 to -2, and 0 to -7. That's it. You replace wherever 2 is there, replace by -3. Wherever -3 is there, replace by 2. I mean, you got it, right? What needs to be done?
So that means we are inversing it, right?
Yeah, that's what it is. So typically 0 to 255 is the scale. If this is my I, the contrast is what? 255 minus I. They made
That
it.
is a negative, right?
Yeah, image negative.
Image negative, right?
Yeah. And yet they made it complicated in the 2's complement.
2's complement of a 4-bit. Okay.
Yeah. So you may get questions in 3 bits, 5 bits, right? So yeah, just remember the concept. That's it. And yeah, I mean, this is a simple question, and we can answer here itself. Which of the following is a local, global, and point operation on an image, right? And why? So convolution with a kernel 3x3 is, take a 3x3 kernel and we do a convolution. So is it a local operation, point operation, global operation? Right? It's a local operation because 3x3 kernel, the kernel is looking at the 3x3 patch of an image, right? And throwing out some value. That's why it is local operation. Cross correlation with 1x1 kernel. Now this is just any cross correlation or convolution with 1 cross 1 scalar is nothing but a multiplication. Right? It's a point operation. It's a point-wise multiplication of
Point-wise multiplication.
and Fourier transform of an image. Right? It's an entire global operation.
Global operation.
Sure product with another image. Sure product is element wise. I have image I and there's an image I1. I compute a sure product of this thing. Sure product typically is denoted something like this. If you treat I as a matrix, sure product of I and I1 is nothing but if there is a pixel 3 comma 4 here with intensity 8 and this is a pixel 3 comma 4 with intensity 9 and they just multiplying 72. That's it. So it's an element wise operation. It's a point wise operation.
Whole image will be
Yeah.
transformed.
Yeah. And flipping the image upside down, right? Even that's a global operation. And yeah, in a sift, to reject some of the filter out some of the key points, so they do this computer Hessian matrix and right, and um, they have a threshold, say 0.3 for a particular candidate point to be accepted or not at a given location. So what do you do is if this is Hessian matrix, you just evaluate this metric trace over determinant and compare with the threshold. If it is more, just reject that point, right?
What will be the threshold value, sir, as per the original value?
I think it's 10 in the paper.
10 in the paper,
That,
and yeah, in the discussion it came 2.0.02, I guess, or 0.2 something.
yeah, something. I don't remember exactly. Yeah, now we have to map which element in set A maps to which element in set B. Okay, so set A has histogram equalization, cross correlation, and a Gaussian kernel. Now set B has local operation, contrastive stretching, and low pass filter. Now, what is histogram equalization? It's a kind of a contrastive stretching, right? Each pixel intensity is mapped to some other value, some kind of contrastive stretching. Now cross correlation is a local operation similar to convolution. Okay, what is a Gaussian kernel? It's a low pass filter.
Almost smoothens out, yeah, low pass filter.
Yeah, it's a low pass filter. Yeah, and if something like Sobel operator comes here, Sobel operator, and this, if there's a high pass filter, you need to choose that appropriately. Okay. Yeah, I think that's it for today. Going forward from the next week, as you guys discussed, we will brief through the that week's content, maybe 5-6 slides, and then we'll go to the programming part, and then we will solve the 6 questions. And I'll check if I can solve the assignments that have been you have already been submitted. Okay.
Yes, so that will be really great.
Yeah, I'll check and I'll solve. I'll try to solve.
Okay.
Okay, guys, thanks for joining, and let's meet next week. And anything that you guys need it, please type in. I'll try to answer next week. Okay. Let's meet next week then.